All right, get ready to unlock some serious math mojo with me today.
Sounds exciting. What are we diving into today?
Today's deep dive is all about cracking the code of linear equations. But don't worry, we're leaving the dusty textbooks behind for this one.
Linear equations. I'm intrigued. You sent over some excerpts from, what was it called? Pair of linear equations in two variables.
You got it. We're going to unravel this together and see how these equations pop up in the most unexpected places.
You know, what always fascinates me about linear equations is how they underpin so many things we take for granted. They're like the hidden framework behind everyday decisions.
Okay, I'm all ears. Give me a real-world scenario. Paint me a picture.
Absolutely. Imagine this. You're at a bustling village fair. Well, it's a little lighter after, I'm sure. Who are we kidding? But you're ready for some sun. Our friend Akila here is trying to decide how many rides on the giant wheel versus games of hoopla she can fit into her budget.
Sounds familiar. Who hasn't been there, right? Trying to squeeze the most fun out of a day at the fair. But how do linear equations play into Akila's big decision?
Well, each giant wheel ride costs €1, and Hoopla sets her back for a game. Akila's got a grand total of 20 to spend.
Classic fairground dilemma. Limited budget, unlimited fun to be had.
Exactly. To figure out the perfect combination of rides and games, we can use, you guessed it, a pair of linear equations.
All right, so we're talking about finding the perfect balance between thrill rides and games of skill, all while being mindful of that budget.
Exactly. And each of those activities, the rides and the games, can be represented by a linear equation because the cost increases at a steady rate. It's like a mathematical balancing act.
I'm ready to dive into the details. How do we turn Akila's fairground dilemma into these, as you call them, magical equations?
Let's use X to represent the number of giant wheel rides and Y for those hoopla games. Since each ride costs 3, the total cost for rides becomes 3X.
Okay, makes sense. So we're basically multiplying the number of times she does each activity by its cost.
Exactly. And similarly, the total cost for hoopla becomes 4Y. Now, we know Akila's total spending limit is 20.
Right, got to stick to that budget.
This gives us our first equation. 3X plus 4Y equals 20. This equation represents all the possible combinations of rides and games that would cost her exactly 20.
Okay, that's one equation down. It's like we've mapped out all the points where Akila spends all her money. But we need another equation, right? We're working with a pair, after all.
You got it. The second equation comes from the relationship between the number of rides and games. Let's say Akila decides she wants to play hoopla half as many times as she rides the giant wheel.
So if she rides the giant wheel 4 times, she'd play hoopla only twice. I see.
You're a natural. We can express this relationship mathematically as y equals half of x, or y equals 12x.
I'm following along.
And to make it fit the standard form of a linear equation, it can be rewritten as by 2y equals 0.
Okay, so now we've got 2 equations, just like you said, a pair of them.
Yeah.
But before we get into solving them, I need a little refresher on what a linear equation actually represents.
Of course. Think of a linear equation as a line you can plot on a graph, kind of like a treasure map.
Ooh, I like where this is going. So are we searching for the buried treasure?
Exactly. All the points on that line are solutions to the equation. The x marks the spot on our map. These equations generally follow the form x plus by plus c equals 0 to...
Hold on. Don't throw too many letters at me at once. What do those letters stand for again?
Don't worry, it's simpler than it looks. The A, B, and C are constants, like landmarks on our treasure map, they stay put, and X and Y, those are our variables, the coordinates that can change, leading us on different paths on our map.
All right, I'm starting to get the lay of the land now. So when we're talking about a pair of linear equations, like in Akila's case, are we essentially trying to find where those 2 lines cross on our map?
You hit the nail on the head. That point of intersection is the sweet spot, the solution that satisfies both equations. It's the place where both our treasure maps agree.
So it's like finding that hidden gem where 2 paths converge on our map. All starting to click now.
Precisely. Now, here's where things get really interesting. When we graph 2 linear equations, there isn't always a single point of intersection. Sometimes the lines, well, they have other plans.
Ooh, a plot twist. I'm all ears. Tell me more.
Picture that the lines could be parallel, like train tracks running side by side. They'll never intersect, meaning there's no solution that satisfies both equations.
So they're like ships passing in the night, never quite intersecting. Okay, last but not least, what about those infinite solutions where every point's a winner? How do we spot the lucky equations?
For those, the ratios of A1 to A2, B1 to B2, and C1 to C2 are all equal. It's like the mathematical stars have aligned perfect harmony across all the ratios.
It's like a cosmic convergence, a mathematical jackpot. Now, I know we talked about graphing these equations to find the solution, but you hinted at other, perhaps more elegant methods. Don't leave me hanging.
You're right, there are. One such method is called substitution, which is perfect for situations where one variable is already expressed in terms of the other.
You mean like how we defined y in terms of x earlier with Aquila's hoopla and giant wheel situation?
Precisely. That's substitution in action. Instead of wrestling with two equations and two unknowns, we streamline the problem by substituting the value of one variable from one equation into the other.
So it's like a tag team match.
Yes.
One variable steps in for the other, making the equation much easier to handle. And once we have the value of that first variable, we can just plug it back in to find the other one, right?
Exactly. It's a two-step dance.
Yeah.
Solve for one, then waltz back to find the other. But substitution isn't our only trick. There's also the elimination method.
Elimination. It sounds almost too good to be true, like a magic act. How does that work?
Remember how we talked about multiplying one of our equations by a constant to make the coefficients match? We can do something similar here. We strategically multiply one or both equations by carefully chosen constants so that the coefficients of one of the variables become opposites.
So if one equation has plus 2y and the other has negative 2y, when we add them together, poof, the y term disappears.
Exactly. It's like waving a magic wand, making one of the variables vanish into thin air. We're then left with a simpler equation to solve for the remaining variable. And just like with substitution, once we've found one, we can substitute it back into either of the original equations to find its partner.
It's like having a whole toolkit of problem-solving strategies. We can choose the best method, graphing, substitution, or elimination, depending on the specific equations we're facing. It's empowering.
I couldn't have said it better myself. It's all about understanding the tools at your disposal and knowing when to use which one. Now, are you ready to put our newfound knowledge to the test and solve Aquila's fairground dilemma?
Absolutely. Let's rewind back to Aquila and those equations. We have 3x plus 4y equals 20, representing her total spending limit, and by 2y equals 0, capturing her preference for the ratio of rides to games. I'm ready to crack this case wide open.
Excellent. Let's see those problem-solving skills in action.
Okay, detective hat on. We've got our trusty equations, and I'm ready to solve for Aquila's ideal fairground experience. What method will help us crack the code this time?
Well, since we already have x conveniently expressed in terms of y in the equation by 2y equals 0, substitution seems like the most elegant approach. It's all about using what we know to uncover what we don't.
Right. I'm with you. Let's substitute. So if 2y equals 0, we can rearrange that to get x plus 2y.
Yeah.
One variable down, one to go.
Exactly. Now we take that value of x and substitute it into our first equation, 3x plus 4y equals 20. So that gives us 3y plus 4y equals 20.
Ah, it's all coming together now. Simplifying that, we get 6 plus 4y equals 20, which becomes 10y equals 20. And if we divide both sides by 10, drum roll please, we find that y equals 2.
That's right. Aquila can squeeze in 2 games of hoopla. Now to find out how many times she gets to ride the giant wheel, we just plug our newfound yay value back into either of our original equations.
True. But we already have x2y, so might as well use that one. Efficiency is key.
Smart move. Substituting y2, we get x equals 2, which means x equals 4. So Aquila can fit in 4 thrilling rides on the giant wheel.
I love it when a plan comes together, especially when that plan involves a bit of math magic. This deep dive has been eye-opening. I never thought I'd look at a village fair and see a playground for linear equations.
And that's what's so fascinating about this, isn't it? These seemingly simple equations have applications far beyond textbooks and fairgrounds. They pop up everywhere, from economics and engineering to fields you might not expect, like computer science.
Whoa, really? I never made the connection between linear equations and something like computer science. How are they used in that realm?
Well, think about computer animation, for example. Creating those lifelike movements and seamless transitions involves tons of calculations based on, you guessed it, linear equations. They're used to model the relationships between different points in space, ensuring those movements appear smooth and realistic.
Wow, that's mind-blowing. So every time I watch an animated movie, I'm basically witnessing linear equations in action.
Exactly. It's a hidden layer of mathematics that brings those digital worlds to life. And it's just one example of how understanding linear equations can give you a whole new perspective on the world around you.
This has been incredible. So for anyone listening, the next time you're at a village fair, strategizing how to spend your money, or even just marveling at the latest animated film, remember the hidden power of linear equations. They're more than just formulas on a page. They're tools that help us understand and navigate the complexities of our world.
Well said. And who knows, maybe this deep dive has inspired you to think about situations in your own life that could be modeled using a system of equations. What insights might those solutions reveal?
It's definitely something to ponder. Until next time, keep those brains buzzing and keep exploring.